Now we're looking at a functor type class. So far we've encountered a lot of the type classes in the standard library. We've played with ord, which is for stuff that can be ordered. We've palled around with EQ, which is for things that can be equated. We've seen show, which represents an interface for types whose values can be displayed as strings. Note on it says the volume is always too loud. I suppose I can see how you can have that bias, yeah. The volume is too loud, so you have to... Got that explosive noise when you start some video or something, it's like, whoa! Yeah. Our good friend Reed is there whenever we need to convert a string to some... to a value of some type. And now we're going to take a look at a functor type class, which is basically for things that can be mapped over. You're probably thinking about lists now, since mapping over lists is such a dominant idiom in Haskell. And you're right. The list type is part of the functor type class. So I assume that functor is lists and trees and whatnot. Oh, did you say that the music was too loud? Was that what you were saying? That better? Maybe. That's probably better. What better way to get to know the functor type class than to see how it's implemented? Let's take a peek. Class functor f, where fmap have function that takes an A and returns a B, and then we take the function A and do the function to B. Alright, we see that it defines one function, fmap, and doesn't provide any default implementation for it. The type of fmap is interesting. In the definitions of type classes so far, the type variable that played the role of the type in the type classes was the concrete type, like the A in... Right, we're back to this again, yeah. In the EQA. Exactly, but now f is not a concrete type, yeah. F is a function, right? A type that can hold a value, can hold like int, bool, maybe string, but a type constructor that takes one type parameter. Wait. Yeah, it's a constructor. A quick refresher example. Maybe int is a concrete type, but maybe it's a type constructor. Right, so f is a type constructor that takes one type as the parameter. Anyway, we see that fmap takes a function from one type to another, and a functor applied with one type and returns a functor type with another type. Right, it's like when we're iterating over a list, right? We take one value and then we change it into some other value that does not have to be the same, right? We can map an int to a string, to a character, for example. And that's a map, a function that does that. We can, however, just say an int plus 1 and b can still be the same. But this I don't quite understand, right? FA into FB. This sounds a bit confusing, don't worry. All will be revealed soon, when we check out a few examples. Let's do it. This type declaration for fmap reminds me of something. If you don't know what the type signature for map is, it is exactly. Map is doing this exactly, since the right, the list is syntactic sugar, right? Interesting. It takes a function from one type, and it takes a function from one type to another and a list of one type and returns a list of another type. My friends, I think we have ourselves a functor. In fact, map is just a fmap that works only on list. Here is how the list is an instance of the functor type class. Instance functor and a list where fmap is equal to map. Interesting. That's it. Notice how we didn't write instance functor a where, because from fmap we see that the f has to be a type constructor that takes one type. Since the list of a is already a concrete type of a list with a type inside it, while the empty list is a type constructor that takes one type and can produce types such as of ints and strings and even list of strings. Since for lists fmap is just map, we get the same result when using them on lists. Oh, look at that. They're the same. What happens when we use fmap on not a list? What happens when we map or fmap over an empty list? Well, of course, we get an empty list. It just turns an empty list of type A into an empty list of type B. Types that can act like a box can be functors. You can think of a list as a box that has infinite amounts of little compartments, and they can all be empty. One can be full and the others empty. Wait. One can be full and the others empty. There we go. Or a number of them can be full. Exactly, yeah. Oh, hello, Colgate on tap. Nice to see you again. Inspirabot says, isn't it kind of obvious that seconds can become pleasant if we learn to think outside of the box? So many times the Inspirabot just starts out, yeah, seconds can become pleasant. Then if you think outside the box, how is thinking outside the box relevant? Who knows? Inspirabot just takes two statements and just glues them together. And it doesn't make sense. So what else has the properties of being like a box? Speaking of boxes, right? Inspirabot knows we're talking about boxes. Is that what's going on? For one, the maybe a type. Right. Yeah, that's like a box, but it can only have one thing in it. In a way, it's like a box that can either hold... Oh, right, yeah, it either holds nothing, in which case it has the value of nothing, or it can hold an item like haha, in which case it has the value of just haha. Here's how maybe is a functor. Definitely a box. How do we map on this? Right, instance functor maybe where fmap f just x is just function x. Oh right, yeah, there we go. And all right, and if we do it on nothing, we just return nothing. Of course we do. Yeah. Colgate on tap says, we are just so far away from the box we don't even realize that we are outside it. Don't even realize, eh? Or maybe you were in a box all along and you just don't see the edges of the box. Boxes in boxes. Again, notice how we wrote instance functor maybe where instead of instance functor maybe m where, like we did when dealing with maybe and yes no. Functor wants a type constructor that takes one type and not a concrete type. Right. I kind of get why yesterday he was so insistent on pointing this out, right? The difference between concrete and constructors. If you mentally replace the f's with maybes, fmap acts like maybe A to maybe B. Yeah, exactly. For this particular type, which looks okay, but if you replace f with a maybe m, then it would seem to act like, yeah, and that's not okay. Maybe MA? I don't know. Which doesn't make any damned sense, because maybe takes just one type parameter, exactly. Anyway, the fmap implementation is pretty simple. If it's an empty value of nothing, then just return nothing. If we map over an empty box, we get an empty box. It makes sense. Just like if we map over an empty list, we get back an empty list. If it's not an empty value, but rather a single value packed in a just, then we apply the function on the contents of the just. Yeah, on the contents of the box. That's what map does. Yeah, it applies it on the contents of the box. Fmap, I mean. Function map, yeah. Hey guys, I'm inside the just. Something serious. Yep. Exactly. I get this feeling that it's all coming together. Not all, well, it's this whole chapter. Well, this, what we did last day is coming together now. Another thing that can be mapped, and the whole mapping business is, that function is coming together a little bit as well. Another thing that can be mapped over and made an instance of functor is our tree. It can be thought of as a box in a way. It holds several or no values, and the tree type constructor takes exactly one parameter. If you look at fmap as if it were a function made only for tree, its type signature would look like boom. Yep. Exactly, we take A to B, tree A, tree B, exactly. We're calling the function on the contents of the tree. There we go. We're going to use recursion on this one. Oh yeah, mapping over an empty tree will produce an empty tree. Mapping over a non-empty tree will be a tree consisting of our function applied to the root value, and its left and right subtrees will be previous subtrees. Our only function will be mapped over them. Colgate InOnTaps thinks that we should do a Code Wars kata right now. In the middle of this? I'm in a little bit of a hurry today. Right, if we got time, let's go down here, and if I have time, we do a kata down here. Since I'm going for an early lunch. Otherwise, I'll have to do the kata tomorrow. First thing tomorrow morning. Instance. Functor tree where... Yeah. Map f on an empty tree returns an empty tree, while fmap f we have node, this is our node x, and we have our left subtree and our right subtree. Right, and we have node, and we call our function on the x, and then we recursively check both of our subtrees. Right, multiply by 2 on our empty tree returns an empty tree, right? multiply 4 by fold right, tree insert on our empty tree. Oh yeah, he's just making a tree to fmap on. Nice. Now how about either a b? Can this be made a functor? Yeah, I mean, either a b is very similar to maybe, right? So it should be a box that contains either a or b. The functor type class wants a type constructor that takes only one parameter, but either takes two. I know, we'll partially apply either. Yeah, exactly, I was thinking that. Partially apply by feeding it only one of the parameters, so it has one free parameter. Here's how either a is a functor on the standard libraries. Right, it's an instance of functor where fmap f function on the right x right, exactly, we apply the function to the right. Well, the left x just right function. Oh, right, it doesn't do anything, because if we're applying it to the right, then we're applying it to the right. Right? Maybe. Well, what did we do here? You can see how we made either a an instance instead of just either. That's because either a is a type constructor that takes one parameter. Yep. Whether either takes two. If fmap was specifically for either a, the type signature would then be B2C either AB into either AC. Yes, because that's the same as, yeah, like we've been talking about, fmap. In the implementation, we mapped in the case of a right value constructor, but we didn't in the case of a left. Why is that? Well, if we look back at how either AB type is defined, it's kind of like, wait, data either AB, left A, right B. Yeah, how does it apply on our other thing? Well, if we wanted to map one function over both of them, A and B would have to be the same type. I mean, if we try to map, we try to map a function that takes a string and returns a string, and B a string but A was a number, that wouldn't really work out. Also, from seeing what fmap's type would be if we operated only on either values, we see that the first parameter has to remain the same, while the second one can change, and the first parameters is actually actualized by the left value constructor. This also goes nicely with our box analogy. If we think of the left part as sort of an empty box with an error message written on the side telling us why it's empty. Maps from data.map can also be made a functor because they hold values, or not. In the case of map key value, fmap will map a function over a map type map kv and return a type of map k, then it changes the value. Why did he put it like this? That's a little bit confusing, isn't it? Note that the single quote has no special meaning in types, just like it doesn't have a special meaning when naming values. It's used to denote things that are similar, only a slightly changed. I suppose that makes sense. Oh shit. We decided we were gonna meet 11:45, and now my mom sends a message and says she's here now. Alright, so just try and figure out how map k is made a functor, an instance of functor by yourself. Right, it's the same as before. It takes two values. It's exactly the same as either. Almost. Pretty much, yeah. With the functor type classes, we've seen how type classes can represent pretty cool higher order concepts. We've also had some more practice with partially applying types and making instances. In one of the next chapters, we'll also take a look at some laws that apply for functors. Just one more thing. Functors should obey some laws so that they may have some properties that we can depend on and not think about too much. If we use fmap plus 1 over the list 1, 2, 3, 4, we expect the result to be 2, 3, 4, 5, yeah. And not its reverse. If we use fmap, then a lambda function, the identity function, which is just returns its parameter over some list, we expect to get back the same list as a result. Yes, that makes sense to me. For example, if we gave the wrong functor instance to our tree type using fmap over a tree where the left subtree of a node only has elements that are smaller than the node to the right subtree, only has nodes that are larger than the... yeah. Exactly, we want exactly the same. We'll go over the functor laws in more details in the next chapters. Right, of course we want it to be the same. We want everything to be in the same spot. That makes sense. Well, GetInnoTap asks, does your mom know Haskell? No. My mom does hardly know how to handle a remote for the TV. Right, but since she's outside, thanks for hanging out and have a good one. Yeah. Cheers.